All right, so I wanted to take a second today and do a quick video on integration by parts. Now, integration by parts is another trick that you'll use to integrate complex functions. Um, Remember that functions always have derivatives. Pretty much every function out there, we have a way to find the derivative, but we don't always have a way to find the antiderivative. When you're looking for the antiderivative, you kind of have to go through the different tricks that you have and see which one might apply and hope that there's one out there that works. And oftentimes in the real world, it's more rare in a math class, but most often in the real world, if you just pick a function at random, it won't have a closed form integral. However, if you can use integration by parts, that means it does. The logic for why the integration by parts works goes back to the product rule. So if you remember, we have the product rule says if I have two functions, f and g, and I take the derivative of them, I get f prime g plus fg prime. And what that means is that I should be able to take the integral of both sides, and that integral is a mathematical operation, so it should leave both sides looking the same. Well, what's it going to be on the left side? Well, the integral of the derivative is just the function itself, so fg is equal to, now I'm just going to split these up, f prime g dx plus integral of fg prime dx. And so what integration by parts says is that the integral of fg prime dx is equal to fg minus the integral of f prime g dx. Now note that both these f and g's are supposed to be f as a function of x. I just kind of didn't write that because it was a little quicker. You might, rightfully so, ask yourself at this point, who cares why that works? Who cares that that works? That's a good question. But I'll show you an example. Let's say I have an example like, oh, I guess before I show you an example, I'll tell you that when you see integration by parts, instead of f and g, you usually see the u with u's and v's, where f represents u and g represents dv. So the technical formula for integration by parts is the integral of u dv is equal to uv minus the integral of v du. So let's say I have an example like the integral of x e to the x dx. And you think, can I make a substitution? Well, if I substitute in for e to the x, my dx is going to be e to the x. That's not going to replace a part. If I substitute in for x, well, that's not going to do anything anyways. So substitution does not work here. So you might start thinking, what else do I know? And the next thing you think, integration by parts. And with integration by parts, you have to pick the u and you have to pick the dv. So I'm going to pick u in this case to be x, and I'm going to pick the dv to be e to the x. So du is going to be 1, dv is going to be e to the x. So now the integral of x e to the x is going to equal uv, which is x e to the x, minus v du, which minus the integral of v du. Some people teach this like it's a lucky 7. So this is e to the x dx. And you're like, why do we do that? Well, now look. Now can I take the integral of e to the x? I can. So this whole thing is going to equal x e to the x minus e to the x plus c. Boom. And there's a basic example of where integration by parts allowed us to do something that we wouldn't otherwise have done. I can give you another example that I remember doing a lot as a student, which is integral of x squared. Let's say x squared sine of x dx. And I just want you to picture what's going to happen when we do this. If we were to do this, we'd have something very similar to this format, and we'd get down to this next step here, and we wouldn't have had an expression that we could entirely evaluate. We'd have to do integration by parts a second time. And there's a point in your life at which you become above the rule, become above having to do integration by parts a second time. And you're not there yet, but I am. So I'm not going to do that for you. However, you should know that it's possible to be done. And you would do it in the same format, and it would take a little bit more work. And it's one of those things that adults enjoy seeing kids do because it was done to us, and now we get to do it to you. And we don't have to do it either. A couple more examples that might throw you off. You might see something like the antiderivative of a trig inverse function, and you might be like, what the heck do I do? How would integration by parts apply there? Well, you could, with any function, you could technically say, oh, it's like 1 times cosine inverse of x, and you could call this u, and you could call this dv, and that happens with CPM. It's unlikely to happen with the AP test, but it could happen. That's a trick that you should know. And then which one should you, but generally, this one defies the general rule, which is which one should you choose for u and which one should you choose for v. So in in this example, this is typically what you might get with an integration by parts. And you're going to have two parts, obviously. You're going to have a u and a v. And one of these is, and I guess, or you could have a v and a u. It's up to you to choose which one's which. But if you look, one of these two things is a function that goes down, like it's a polynomial function. So if you keep taking the derivative, it's going to go down to 0. And one of them is a repeater. Okay. So the one that's the repeater is the one that's going to go into as dv. The one that's the descender is the one that's going to go in as u. I'm going to give you another example of what happens when you get a repeater, but I'm going to save that for a second video.